Welcome to ACCA F5 Performance Management. I'm called John Ntende and I'll be your tutor throughout this session. I can be reached on john.ntende@gmail.com or on telephone number +256 788 4375 43. You can also find us at Management and Financial College at the following website, www.mafuganda.com. Now today we shall be looking at an interesting topic which is called linear programming. It's a key technique which we can use in this paper, and it's a key examinable area. Okay, let's start by understanding what linear programming is all about. Now, linear programming is a technique, and the best way to illustrate it is by using a simple example. So imagine you own a home baking business, and this business makes two products, cake and bread. The selling price for cake is $18, and the selling price for bread is $24, and the variable costs have been given as 16 and 21. Now let's also say that there are two key processes. One is mixing and the other is placing the product in the oven. And so let's say that the cake takes 0.6 hours mixing time, and then they also say that the bread takes 0.8 hours mixing time. Let's also say that the cake takes 0.4 hours in the oven and the bread takes 1.2 hours in the oven. Now we're also told that the oven time is 2,400 hours per year. So what we're seeing here is an example of a constraint. So a constraint means the same thing as limiting factor. It is basically something which prevents us from achieving our objective. Now the objective of any business is to make profit. So anything which prevents you from achieving as much profit as you can is what they call a constraint. So in this case it is the oven time. So that's one constraint. Another constraint which has been given is the mixing time, and it could be because of the labor constraints. So the mixing time is limited to 2,400 hours per year. So that is constraint number 2. The minimum demand has been set at 1,000 per year. And the maximum demand for bread is 1,300 per annum. So you have a business which is making cake and bread, and it is subject to 4 constraints. So the question we need to ask, which linear programming can help us solve, is how many cakes and units of bread should we make? So you see here we're trying to maximize a certain objective, which we shall look at in detail, for a given business which is subject to all these constraints. So let's see how we can use linear programming, which is a technique to help us obtain the optimal production mix to achieve a certain objective. The objective in this case is trying to maximize the profit. So let's see what exactly we would do to solve this problem. So we need to have a systematic way of formulating the problem. Now in ACCA, the best thing is to always have a key set of tools. So when you see a question relating to linear programming, you know that you have a standard set of steps you need to use to solve the problem. So the standard set of tools you need to solve the problem is: 1, you define the variables. So if you're in an exam, clearly have a short heading, define variables, and go on to define what the variables are. Now we're trying to decide on how many cakes and on how many units of bread we should make. So the variables are the cake, the number of cakes, and the number of bread. We also need to establish the constraints. The constraints we've already been given. We shall see in detail what the constraints are. Then the objective function. Remember I told you our objective is to maximize profit. So that will be our objective function. We shall see in detail how to get the objective function. Then eventually we draw the graph. We plot the constraints on the graph. After doing that, we determine the feasible solution. After determining the feasible solution, we now find the best solution. The best solution is the one which optimizes the objective function. So we need to find the best solution from the feasible solution, which optimizes the objective function. So the objective function is usually to maximize profit or to minimize cost. Okay, let's move on. Now we said we need to define the variables. The variables are the number of cakes. So you let C equal to the number of cakes. Now this C could be anything else, which is convenient. So I'm using C because it's the first letter of cakes. So you let C equal to the number of cakes, and then you let B equal to the number of bread. So C and B are our two variables which we're trying to find. The next step is to establish the constraints. Now there were 4 constraints. One was oven time. Now oven time was limited to 2,400. Okay, so each unit of cake took 0.4 hours and each unit of B took 1.2 hours. So the total time in the oven would be 0.4 C plus 1.2 B. Okay, and this should not exceed 2,400. That's why we have the sign of less than or equal to 2,400. So the oven time should not exceed 2,400. So the equation is 0.4 C plus 1.2 B should be less than or equal to 2,400. The next constraint was mixing time. So again, it was limited to 2,400. So again, we have the same sign here, less than or equal to 2,400. Each unit of C takes 0.6 hours. Each unit of B takes 0.8 hours. So the total time for mixing is 0.6 C plus 0.8 B. And so this should not be less than or equal to 2,400. The next constraint was on cake demand. We were told that cake demand is a minimum of 1,000. So whenever you say here minimum, it means the symbol to use is greater than or equal to. So the equation is C should be greater than or equal to 1,000. The other constraint was on bread demand. This time we are told that the bread demand is a maximum of 1,300. So whenever something doesn't exceed a certain figure, we use less than or equal to. So bread demand should be less than or equal to 1,300. Then there are what we call the non-negativity constraints. So C and B should be both greater than or equal to 0. So you cannot have negative units of tangible products. So C should be greater than or equal to 0, and then B should be greater than or equal to 0. So here we have the constraints: oven time, mixing time, cake demand, bread demand, and non-negativity. Okay, let's move on. The next step was to determine the objective function. Now, I told you the objective is to maximize profit. From the information given, we can calculate the contribution, which is simply the selling price less variable costs. So contribution is very similar to profit. So in this case, we're going to use contribution, which has been given as the selling price minus variable cost. So we have two products, cake with a selling price of 18. So 18 less 16 should equal to 2. So the contribution per unit for the cake is $2. Now for bread, it's 24 less 21, which gives us 3. So our objective function, which is the contribution, should equal to 2c, okay, because each unit of cake makes $2, plus 3b because each unit of bread makes us $3. So our objective function is contribution is equal to 2c plus 3b. So we're going to try to find values of c and b, which give us the highest possible contribution, subject to the constraints we've already looked at. Next, we have to draw the graph by plotting the constraints on graph paper. Now, in an exam, you'll be given graph paper, so it's very essential that you practice how to draw this information accurately on a graph paper. Before we do that, we need to plot the following constraints. Now, 0.4c plus 1.2b is less than or equal to 2,400 is a straight line. So this equation is a straight line. You have two variables and you have this figure here. So this is a straight line, and if you remember, in order to draw a straight line, you need 2 points on that line. So you can let c be anything and find the corresponding value for b. The easiest thing is to let c equal to 0 and find the corresponding figure for b, which is 2000. Then you let b equal to 0, meaning that this figure goes out, and then you have 0.4c being equal to 2400. That means that c, if you divide both sides by 0.4, c will be 6000. So there are 2 points on this line. When c is equal to 0, b is 2000, and when b is equal to 0, okay, c is equal to 6000. So we do the same thing for mixing time. When c is equal to 0, b is equal to 3000, and when b is equal to 0, c is equal to 4000. So once we have these 2 points, the next thing is simply plot them on graph paper. So let's draw the graph in detail. The first thing you need to do is to draw the axis. So you draw a vertical axis, you draw a horizontal axis, you name the axis. Now in this case, my vertical axis is c. It doesn't matter whether it's c or b. My origin is O, so that's the point 0, 0, 0 c, 0 cakes, and 0 bread. Then you of course name the horizontal axis as b. So now we need to draw these lines on our graph. So we need to draw the line for over and over time, which was 0.4c plus 1.2b is equal to 2400. Now remember, we say that when c is equal to 0, b is equal to 2000, and when b is equal to 0, c is equal to 2000. So we plot these 2 points on the graph. So this point here is the point when b is equal to 0 and c is equal to 6000. and this point here is the point when C is equal to 0, B is equal to 2000. So we join these 2 points by a straight line. So that straight line is the line for oven time. Next, we draw the line for mixing time. Now we're told the points C is equal to 0 and B is equal to 3000, and B is equal to 0 and C is equal to 4000 lie on that line. So we plot the points. This point here is the point B is equal to 0 and C is equal to 4000, and this point is C is equal to 0, B is equal to 3000. So you join these two using a straight line. So you use a ruler and pencil and join the 2 points. So that's the line for mixing time. Next is the bread demand. B is equal to 1300. So this is a vertical line passing through the point 1300. So we draw a vertical line passing through that point. So that's the line for the bread demand. Next is the line C is equal to 1000, which is cake demand. So it's a horizontal line passing through the point C is equal to 1000. Now 1000 is somewhere on this side, so a horizontal line passing through that point is the cake demand, which is C is equal to 1000. So there we have it. We've drawn the line for oven time, for mixing time, for bread demand, and for cake demand. So the marks for, of course, drawing the lines accurately, for labeling all the lines, and for labeling the axes. Okay, next we need to establish the feasible region. Now we need to shade off the unwanted areas. Now let's start by shading off the non-negativity areas. So we don't want anything less than 0. So anything this side is 0. So this side is definitely unwanted. We don't want anything which is equal to negative. Okay. Now let's go to oven time. Oven time, this is the line over here. We're told oven time 0.4C plus 1.2B should be less than or equal to 2400. So we're not interested in anything which is greater than or equal to. And this side on the right represents the greater than side. So we're shading off the unwanted region. We're going to do the same thing for mixing time. We're told that mixing time should be less than or equal to 2400. So we shade off the upper side just like this. So this side represents the greater than side, and we're not interested in this. Bread demand, we're told that bread demand should be less than or equal to 1300. So once again, I'm not interested on the right, because all figures beyond this are greater than 1300. And then finally, we're told that cake demand should be greater than or equal to 1000. So I'm not interested in anything below 1000. So anything below this, I'm not interested. So the region which is unshaded, which is the region A, D, E, F, and D, is the feasible region. So the region AD, this region here, AD, E, F, G, is what they call the feasible region. So our solution is either A, D, E, F, or G. So we need to find the best solution. So how do we find the best solution. Now we draw what they call an ISO contribution line. To do that, we've been told that the contribution is 2C plus 3B. So you let this contribution equal to any random number. So in this case, our random number is 6,000. Remember, 6,000 is a random number, so it can be anything. It can be 3,000, it can be 10,000, it can be 12,000. It is any random number. So what we end up is a straight line. The straight line is 2C plus 3B is equal to 6,000. So remember, if we want to draw this line, we need 2 points. So when C is equal to 0, B is equal to 2,000. When B is equal to 0, C is equal to 3,000. So we plot these points and join them with a straight line. The point B is equal to 0, C is equal to 3,000 is right here. And the point C is equal to 0 and B is equal to 2,000 is right here. So you join these two lines by a straight line. So this line here is called the ISO contribution line. ISO contribution line. Now to find our best solution, the optimal solution, we shift this line upwards, okay? And the last point it touches within our feasible region is the optimum point. So in this case, the last point this line touches is the point E, okay? So this point here, point E, is the feasible solution. Now if your graph is accurate, you can read off the best solution. So by drawing a vertical line, you read off the value of B, and then also by drawing a horizontal line somewhere here, you can read off the value of C. So those two values of C and B, those two values of C and B become your optimal solution. But we can also calculate by solving two simultaneous equations, by solving this equation here, okay, and also solving this equation simultaneously, because point E, the point E is the intersection of this line here, of this line, and then of this line. So we are going to calculate, solve simultaneously these two equations to find the values of C and B. So how do we do the simple computation? Now the two equations are 0.4C plus 1.2B is 2,400, and 0.6C plus 0.8B is equal to 2,400. So we multiply the first equation by 3 and the second equation by 2, which gives us equation 3 and equation 4. So you can see that the value, the figure before C in equation 3 and 4 is the same. So if we subtract equation 3 less equation 4, we end up with 2B is equal to 2,400. So if we divide both sides of this equation by 2, so if we divide this by 2 and divide this by 2, we end up with B is equal to 1,200. If we substitute B is equal to 1,200 in equation 1, we end up with C is equal to 2,400. So B, the number of bread, the number of loaves of bread, or the number of units of bread we should make is 1,200, and the units of cake we should make is equal to 2,400. And so that is our best solution. That is our optimal solution. So we've answered the question. So we need to make 1,200 units of B, of bread, and 2,400 units of cake in order to maximize the contribution. subject to the constraints which we were given. To end it all, whenever you're doing F5, you must have a set of tools. Now in linear programming, the set of tools are: 1, you define the variables; 2, you establish the constraints. In this case, we had mixing time, we had oven time, we had cake demand, bread demand, and of course the non-negativity constraints. Our objective function was maximizing of contribution. So the contribution was 2c plus 3b. Then we drew a graph. We plotted the constraints on the graph. By shading off the unwanted region, we're able to find the feasible region. Within the feasible region, we found the best solution by contributing an ISO contribution line. By sliding it outwards on the right hand side, the last point is touched, which was point E, was our best solution. Finally, we used simultaneous equations to get us the value of the optimal solution. Okay guys, thanks for listening to me. I've been John Ntende. You can reach me for some feedback on john.ntende@gmail.com. Okay, we meet next time. Thank you.